Alrighty, guys, can you hear me?
Yes, I can hear you.
Welcome back. Are there? We have a few minutes before we get started. Are there any questions or comments?
I just wanted to confirm that the final will follow the same format as the midterm. So like we'll start with the question from the list and then like you'll ask follow-up questions from there.
Yes.
Okay, thank you.
So one difference between the final and the midterm is that the midterm, there was a main, there was the midterm also served for you guys to get some feedback, so you could that you could try to take into account for the remaining part of the semester. And for the final, that's kind of it, right? There's no, I mean, the course is over after the final for everybody, and so this is kind of like the last chance to display the knowledge that you have, and so that is a difference between the way that it works. Like the final, this is when we're done with the final, then I have all. There's not going to be any more information to take into account before this assigning grades, and for the midterm this was different. Are there any other questions? Okay, guys, I think it's time to get started. So again, hope everybody had a good break. It's getting closer to the end of the semester, and more or less as usual in my classes, we were running way behind. So see if we can make up for some of it. Today we're going to be talking about Gesanov's theorem. So no doubt about it, Gesanov's theorem. This is a main tool in quant finance, continuous time quant finance. So and what this is about is you start out with a Brownian motion. Start out with a Brownian motion on the P. So you have a stochastic process, and it has a structure for Brownian motion. So the increments are independent, and they are normally distributed, and this all happens under the measure P. And then what happens is that you change measure. So then you're going to have that, you're going to define a new. So then you're going to be given a positive martingale. A positive martingale ZT. Starts out at 1, and you have a measure, and so let's call it P tilde. P tilde satisfies that P tilde on a set A can be computed using this as the Radon-Nikodym derivative process. So this is P of A, P tilde of A is equal to integral of A of, say, CT dP, and this is for all A in FT. Right, so we say, in other words, dP tilde dP, this is equal to CT on FT. Okay, so the dynamics, this CT here, this is our Radon-Nikodym derivative process. So we call CT the Radon-Nikodym derivative process. And we consider, so we're going to write, C's dynamics as, right, so it's going to be a martingale. It's a positive martingale. So we're going to write C's dynamics as dCt. And here we're going to put in a minus sign, and then it's CT. And then what we're going to put here is going to be, I don't know what letter to use. It varies a bit. Let's call it theta dBt. Okay, so Z is here, and then there's a theta. Right, and again, it starts out at 1. So we write Z's dynamics as this, and we call theta t for the market price of risk process. Okay. We should just note here that this equation here is linear, so we can solve. Let's say star here. We can solve star. We can solve star, and the way that we do that is we come up with a guess, and then we apply e to lemma, and prove that the guess works. So we're going to make the guess, and the zt is going to be equal to the initial value, which is 1. There's going to be an exponential. There's a minus sign here. We're going to get the stochastic integral of theta with respect to the round in motion, and then minus 1/2. And then the quadratic variation of the stochastic integral, theta squared du. And we should just check here that this is consistent. This is consistent. This is consistent with an early example where say theta t would just be 1. Right, in that case, when you have theta just to be 1, you're going to get that ct is an exponential, and then you're going to get minus bt, and then you're going to get minus 1/2 integrate 1 from 0 to t. We had that one before.
Why is the consistency important? What's it showing? That it because it's consistent.
Well, you knew that this one here was a positive martingale, right?
Mm-hmm.
Right, we proved that a while ago. Right, so now here there's a more general one.
Oh, okay. So it's like because it's saying it's a more general version.
It's more general, yeah. Right, so it's consistent with the simpler case. Oh, there was another question up here. Nikita's asking, what's the difference between a normal martingale and a positive martingale? I'm not sure. So normal martingale, we haven't talked about normal martingales. But you see, by putting this z over here on the right hand side, this is going to become positive, right? Because it starts out somewhere positive, and then just imagine that it would drift down. So if it were to drift down to say 0, then what would happen is that if c were to become 0, then the change in z would stay there. So by looking at this form where you have dz is equal to z times something, you guarantee that the solution is going to be positive. It's a little bit like an ODE. When you have an ODE of the form f prime t is equal to, say, a constant times f of t, right? This thing here is going to be positive. You say f0 is equal to 1. Right? Because if the solution, if f of t at some point would drift down to 0, if it would do that, right, then f is going to drop to 0. So that means that the derivative is 0. Right? So that means that it's going to stay here. So by having f in this linear fashion on the right-hand side, you guarantee that the solution, if there is one, is going to be positive. And indeed, you see it here, right? This is an exponential function, so this is positive. If I would not have the c on the right-hand side, then that won't work anymore. Does that make sense? So how do we check that this process here, right? There's no z on the right-hand side. How do we check that that indeed solves that one up there? Well, the way that we do it is we apply Ito's lemma. So to check that this is true, we're going to write. So let's write zt as an exponential of say xt, where xt is just what's inside the exponential. So xt is what's inside here. So this is minus an integral from 0 to t theta dbu minus 1/2 0 to t theta u du. Right, and so to apply Ito's lemma, I need to know what dx is. So I throw away the integrals. I put in a minus theta t dbt minus 1/2 theta t squared dt. And then I'm in good shape to apply Ito's lemma. So Ito's lemma gives that dz, what is it going to be? Well, I have to take the derivative of the exponential function. Okay, that's the exponential function. So I'm going to get ext here and then dxt. That was the first term. And then because there's Brownian motion inside x, we need the quadratic variation. So we have to have plus 1/2. And then we need the double derivative of the exponential function. But the double derivative of the exponential function, this is going to be just the exponential function. So we're going to get that one here. And then we need the quadratic variation of x because there's Brownian motion inside x. And so we'll write out now what we have here. This will be ex, that will be my z. Dx, that's the stuff we have up here, minus theta dbt plus, oh, it was minus 1/2 theta t squared dt plus, and here comes the quadratic variation term, 1/2 ct, and then the quadratic variation of x. Quadratic variation of x, we only need to focus on the Brownian motion term. There's no quadratic variation coming from the dt term, so we need to square the integrand. That's going to give me theta squared, and then the quadratic variation of Brownian motion, this is dt. And now we see the terms they cancel out, and we just left with minus z theta dbt. Which is star. So now at least we know what the solution to this linear SE is. It has this nice exponential form. Okay, so that's the starting point for Giesano's theorem. So you have a Brownian motion, and you have one of these positive exponential martingales. That's what goes into Giesano's theorem. So Giesano's theorem will now tell you. So theorem, and this is Giesano. It says so let CT have this exponential form. So we let this thing be a martingale. Then and we're gonna let p tilde be a measure such that such that the radical derivative is equal to zt on ft. And then the miracle happens. Then we're going to get a new Brownian motion. Let's call that b tilde, b pt p tilde. This object here. So this is the definition. This is equal to the Brownian motion that we had before, and then there's going to be a correction term. There's going to be a correction term, and the correction term is this interval from 0 to t of theta u du. And this object is a Brownian motion under p tilde. Right, so it's going to have independent increments. It's going to have normally distributed increments, but now under the measure p tilde. So Alice is asking, where is this correction term coming from? Yeah, so Alice, so when I was preparing this lecture here, I would normally go through the proof, and then we would see where it's coming from. And I know some of you would rather see examples. So I'm a little bit torn now. So now you would like to see where the correction term is coming from, and there are students in here that would like to see examples. So maybe I can give you a hint. So if you want this to be a Brownian motion, at least, so in the proof, so we should at least check. We should check here that this b p tilde is a martingale, because we know Brownian motions are martingale. But then we use Bayes. Bayes says that bt p tilde, this is a p tilde martingale, if and only if what? Something is a p martingale. What is it we have to write here? We should write something with bt p tilde, and what else should we write?
The correction term?
We need to have a connection between the two. Yeah, Timon, you're right. You should write CT. So that's Bayes' rule. And so if I want to check that this is a martingale, I need to check that this is a martingale on p tilde. Okay, so I need to check that this is a martingale on the p. So you take the product rule, you apply Ito's product rule, and you compute the dynamics of the product, d of bt p tilde ct. Keep in mind, now there's a Brownian motion in both of these terms. So there's going to be the usual terms when you do the product, right? You will get bt p tilde dc. And then you do the opposite, ct dbt p tilde. But now we have Brownian motion in both z and b. So you're going to get the cross variation term as well. You're going to get b p tilde crossed over with z. And Alice, this is the magic term. This is where the correction term comes from. Well, let's see that out. So we have dz. that's the one we already talked about. This one here will be theta t ct dbt. This is good because I want to get a p martingale. That one is working because it's a Brownian integral. This one over here with this guy, what do we have there? Well, we need to take d of this guy will be dbt plus, and then d of this thing will be theta. And then we get the cross term. We need to look for Brownian motion terms. Inside B, P tilde, there's a Brownian motion there. And inside Z, inside C, we need to look at DC. Where is he? DC was here, right? So there's a Brownian motion term. So we need to cross them. And you can see what you're going to get. You need to multiply the integrands. You need to multiply the integrands. So here the integrand is minus z theta. Okay, so we're going to get that one over here, minus c theta. And then the other integrand here, that's just a 1. Okay, and then the cross variation between the two objects, that's the cross variation between b and b, that's dt. So you see, Alex, this is where the magic happens, because this dt term here, the dt term here goes away, and notice one here goes away. And so what you're left with will be a Brownian motion term and a Brownian motion term. And both these Brownian motion terms are d martingales. And so if I didn't do that correction, if I didn't have a correction term here, if this term was not there, this term wouldn't be here, and I'll be stuck with this quadratic variation term down here. And it would not be a martingale. Right, so this is not the full proof, so this should really be in quotation marks. But at least it shows you, if I want to have a martingale, I need to have a correction term. I hope this gave you some idea about where the correction term is coming from, Alice. There's more to be done here, and maybe it'll be better to, if you wanted to see more detail, maybe it'll be better to do some of these extra details in office hours. I'm happy to provide, but at least this here gives you some idea about why we need a correction term. Well, I want this to be a Brownian motion, okay, so it should be a martingale. If I want it to be a martingale, then this thing here has to be a martingale, but under P, and then we just use the product rule, and we see that there's a term that needs to cancel out. Okay, so then that's why we have the correction term. Okay. So the last part of the lecture, I had a number of examples in mind, a number of applications. A lot of these applications are old exam questions. So the first one is so BT is a Brownian motion, and so of course we know when we compute the expectation, right? So let me write a P here, even though we don't normally do it. I say that I write a P here, then this will be 0. So the first line of attack could be for you to construct P tilde such that the expectation under P tilde of BT would be say T. So clearly P tilde is not the same as P, but nevertheless, how would we do that? Well, we would use the formula. So construct P tilde, maybe we should have an equivalent measure here, so we can construct P tilde being equivalent to P. So what we're asking for is, so in other words, And that's how it always goes. If you're being asked to create a measure, the thing that you really have to do is to create this theta t, this market price of risk. That's really, the questions are always formulated as construct these measures, but really what you want to do is create this theta. So how would we create this theta? Well, you create this theta by, so Gisano says that BT plus that integral of theta, this is a Brownian motion. Under this measure, P tilde, right? Where the Radon-Nikodym derivative is equal to this exponential e to the integral 0 to t theta u dbu minus 1/2 theta squared on ft. So Gisano's theorem says that this is a Brownian motion. Okay, so if that is a Brownian motion, I'm interested in computing the expectation up here. Then I will get that E of P tilde of BT, but I'll be able to write that by adding and subtracting that integral of theta. So I'll write this as BT. Write that as BT. So I was playing soccer with my kids today, and we had this exercise where we were seeing who could sprint the fastest backwards. So when you hit like your mid-40s, it is a really, really bad idea to see if you can outrun your kids running backwards. And I tripped and I just banged my neck and upper body. Oh, and riding is not helping. Okay. So you have your BT. If I want to get a Brownian motion over this thing, I add the correction term. So we add that up. And then we subtract it away again. Right, and this is what we want it to be t. So we want this to be t. And this here is now a Brownian motion, so this has expectation 0. So I'm left with this thing over here. So what should we choose for theta?
One half t.
Can you say that again? I couldn't hear you. Go ahead.
1/2 t.
1/2 t?
Goes under p tilde.
You want to have it to be, so maybe I should have said this thing not just for 1t. I want this thing to be true for all t. Right, so t is not fixed.
What does the tilde p tilde p mean? Construct p tilde p.
Equivalent.
Oh, okay.
Equivalent.
Equivalent mean like absolutely continuous. Am I remembering that correctly? On like for
Yep.
both or okay.
Equivalent, right? So you have that p tilde is absolutely continuous with respect to p, and p is absolutely continuous with respect to p tilde, or equivalently, is CT is strictly positive. So you're close here. But we cannot theta. We should not have theta depending upon t, because I want this to be true for all t. What could we pick? What could we pick the market price of risk to be? I need t here. I have that. What could I pick theta to?
Can it just be a constant?
And what constant do you want, Ibrahim?
-1.
Yeah, that works.
Okay.
So this here, I should say here, pick for example.
So it's okay as long as it's a constant.
No, if you pick 5, it won't work.
Why does -1 work here?
Right? If you pick theta to be 5, then you're gonna get 5t on this one. Right? You want it to be t.
Oh, okay, I got you. Sorry. Yeah, it's so okay. Yeah.
Okay. Okay, other questions or comments on our first example with Gisanov theorem? Every single problem that's going to follow from now on are probably going to involve Gisanov theorem one way or another. Each's lemma and Gisanov theorem, that's kind of the name of the game. So the next one I had in mind was, let me just share my screen so we can see it. The next one is 15.5. 15 number 5. So here there is a measure. Here there's a measure on F1. And so you have a Brownian motion, which is B. And your goal or your job is to write down the Q dynamics of B. That is, write down, decompose B in terms of something that has a dt term and something that has a deep Brownian motion term. So let's try to do that one. So 15.5. This is on the exam sheets. Let me just stop sharing so you can see my screen better. This is on the final sheets. So you are given now that on F1, you're given that dq dp is equal to e to the b1 divided by e to the, right, it has to start out at 1. It has an expectation 1. So the first thing you need is the, you need the Radon-Nikodym derivative process. We always have to find the market price of risk. This is the name of the game. So we need the Radon-Nikodym derivative process. The Radon-Nikodym derivative process, that's the martingale, right? That's the martingale. That's my ZT. So I know that Z1 is equal to EB1 divided by So I know that C1 is equal to that. And then you use, and you know that it's a martingale. You know that CT is a martingale. It's a positive martingale. As Nikita pointed out, this is a positive martingale. So we need to write the dynamics of DZ exactly in this form we had before. So the first step is to figure out what is a CT. Well, if it's a martingale, I know that CT is going to be the conditional expectation of C1 given Ft. Right, so take a T that is less than 1. If it's a martingale, we know that this is going to be true. Well, then we can presumably we can work out what this conditional expectation is. I think this is also a thing that we did in the very beginning, right? The constant here, he can go outside the conditional expectation. And then we're left with e to the b1 given ft. And how do we compute this conditional expectation? The first one, this is the moment generating function for a standard normal evaluated at 0.1. So this is equal to e to 1/2. What about this conditional expectation? How do we get him computed? How do we get this thing here computed?
Can we do increments?
Yes. Ibrahim, you've done that a lot of times, huh?
Yes, a little bit.
Would it be a surprise if you need to do that on the final?
No.
Okay, so we do -1/2. So we do, what do we do? We do minus BT plus BT.
Yeah.
Yeah, and so then this part here comes out e to the BT, and then it's independent. E to the B1 minus BT given FT. Okay. And so now we can drop this conditional expectation because it's independent. And so here we have a standard normal. So it's the moment generating function just like this one, e to the -1/2, e to the BT, e to the 1/2, and then the variance is 1 minus t. And let's see, there's a half here, there's plus a half there. It cancels out, we get EBT minus 1/2 t, which is one of our favorite martingales. It's one of our favorite martingales of all time because we already had it on the previous slide. Remember this one? And minus BT minus 1/2 t. And here it comes out again. We don't have a minus sign here, but other than that, we're good. So we can actually use what we had over here. We can actually use what we had over here to figure out what DZ is. Right, because if I have a Z of this form, then the dynamics are going to be like that when theta is equal to 1. Right, so from before, we would know that D, or what was it? It was e to the minus BT minus 1/2 t. You would know that this would be equal to minus CT theta t, and this was a 1 dBT. So what would we guess now? dE of BT minus 1/2 t. What should we guess we're going to get here? There's a minus sign here, and there's a minus sign here. Now there's a plus. Well, we could apply Ito using Ito's lemma. This here is a martingale. This thing here is a martingale. We know that it's a martingale, so I don't have to worry about higher order terms. I'm just going to go for the derivative with respect to bt. This is going to be e bt minus 1/2 t, and then dbt. We know the rest of the terms will cancel out because it's a martingale. There can be no dt terms here. So we're going to get that dct in our case is equal to zt dbt. So you see this minus sign that's sitting right here. This is what gave that minus sign that's sitting here. And now we have a plus sign, and there's going to be a plus sign here. So the market price of risk in our case, so the market price of risk this is -1. And then Gesano's theorem, it will give us, Gesano's theorem gives us that bt, and then minus an integral from 0 to t of 1 du. This is a Q Brownian motion. So we can call this, for example, BQ. And this will give us the decomposition that we're looking for. Because if I want to write dBT, I can write this as, well, dBT minus dt plus dt. And what I have here is exactly this Brownian motion. It's exactly this Brownian motion. So that's my decomposition. So whenever you're dealing with your Gesano's theorem, you got to get this Wernicke derivative process, and you got to compute the dynamics of it. And what you need is to write dz, and on the right-hand side, you have to have z times something dbt. And it's that something that's the market price of risk, up to a minus sign. Any questions or comments? I have a couple more prepared, so maybe we should do another one. Let me share the screen again, and then we can have a look at the next one. So the next one I had in mind was number 2. No, it's number 3. Number 3. The next one is number 3. So we're giving a process y. This is geometric Brownian motion that we had before. dy is equal to y dt plus dbt. And so the first, let's skip the first question that we already had stuff like this in previous lectures. Let's skip the first one and go down to questions 2, 3, and so on. Find an equivalent measure such that y becomes a martingale. Right, you have it up here. Y is not a martingale on the P because there's both dt and dbt. Okay, so let's start out with that one. So this was number 3. So number 3.2, we're starting out with a y process. dyt is equal to yt dt plus dbt. So your goal, your job is to find a measure. Your job was to find or construct, I should say, construct Q equivalent to P such that Y has the dynamics YT dBTQ, where BTQ is a Q Brownian motion. Okay, so the way that we do it, it's the usual form. So you need to construct, in other words, construct theta t. This is the market price of risk. Construct the market price of risk. Okay. And how do we do it? Well, we know that we're going to get a new Brownian motion using Yasana's theorem. This will be the old one plus an integral from 0 to t of theta u du, the correction term that Alice talked about. There should be no d here, it should just be bt. So I want this. So what do? I plug in what this part there is. This here is equal to dbt plus my theta dt. So what should theta be? Well, I want this to be the same as that. If I want this to be the same as that, then I should have theta be
one.
very good. Not hard, right? The next question, don't worry, you get harder, Richard. So there's more to practice on here. So now in number 3.4, it says create yet another measure, define dq tilde dq, and there's a formula. Define it to be y1 over y0 on f1 and compute y's dynamics under q tilde. So just a sanity check. We are moving, first we moved from P to Q. And now we're moving from Q to Q tilde. So we're going to get yet another Brownian motion. Let's see if we can figure out what it is. So we need the random derivative process. We always need this one. So it's page 8, page 9. So what we need the conditional expectation. And now we're working downstairs is a Q, so we need to put a Q here. And then you have my Y, we have the Y1 over Y0 given Ft. We need to figure out what this is. Okay, what is it equal to? Well, I know what the dynamics of Y are. dy is equal to Y itself, dBt. But that's the form that we've had a few times. If we just go one back. Just go about one back and you look at your C here, dz was equal to z dbt. It's exactly the same form as we have up here. dy is equal to y db. Okay, so that's a Brownian motion on the Q. This is a Brownian motion on the P. It's exactly the same form, so it's going to have exactly the same solution. And the solution was this one up here, ebt minus 1/2 t. But of course, you have to replace the Brownian motion B with the Brownian motion BQ. So we're going to get the y is a constant, so we're going to get 1 over y0. I'm going to get the expectation on the Q of e to the, and then we take the solution from before. Take the solution from before, it was this one here, just copy him in. It'll be B, we had time 1, so it'll be B1, and now we have the Brownian motion BQ minus 1/2 given Ft. And we know that is a martingale, so we have 1 over y0. And we have e of b1 will become bt, q minus 1/2 t. So we're going to get here, this will be y t over y0. So that's my z. And if I want to figure out what the market price of risk is, I'll compute what dct is. It'll be 1 over y0 dy. And I know y is a martingale. I'll get here that this will be yt. This will be e to the bt q minus 1/2 t, and then dbtq. There are going to be no dt terms over here, and the first two parts, they combine neatly. They combine. I should not write yt here. This is wrong, right? This is not yt. This here is. This I should not write that. I should write. I should use this formula: 1 over y0 d of e to the bt q minus 1/2 t. And these two terms here, they combine neatly into z, ct dbtq.
Wait, can you move that up a little bit more?
Yep. So what's my market price of risk now? this is so the market price of risk in this model is maybe I should call it what is the coefficient that I need DC to be equal to minus I need to write this here with a minus something CT. So what should the market price of risk be? Well, there's a minus. It always has to have this form if you want to use Kisana's theorem.
Is there some like theta
Yeah.
sub t
But there should
in
be a
there?
minus sign here, right? So we should have a minus, and then what's your theta here? Right, if I want to write this here as minus, say, theta t tilde ct dbtq, what would your theta be?
-1.
-1, right?
Yeah.
Okay.
Then Gisano's theorem, and Gisano gives a Brownian motion, which we'll call dbt, and then now q tilde. What is it equal to? Well, it's equal to the previous one. The previous one was the q1. And then we have to add the market price of risk. The market price of risk is -1. So this is going to be this one. So we really have a string of measures. You know, we have a bunch of different measures. We have a measure P. Under the measure P, we're given that dyt is equal to yt dbt plus dt. Right? This was given. Then the first thing we did was create the measure Q. First thing we wanted was to create the measure Q, if I can find it somewhere. First thing we did was to create a measure Q. And this would give us dyt would be yt dbtq. And now we created a measure Q tilde. So what is the decomposition of y under the measure Q tilde? Well, measure Q tilde says there's a connection between Q, the Brownian motion on the Q, and the Brownian motion on the Q tilde. So we can write dyt, this is equal to yt dbtq, which you can write as yt and move this dt to the other side. dbtq tilde. This doesn't look right to me. This doesn't look right. Did we mess up a sign somewhere? So we write this one, plug them in, you're going to get plus dt.
Professor, I have a question. So is the point of Girsano's theorem to change the measure that a Brownian motion like is under to another measure that's equivalent to the first measure?
Yeah.
To put the Brownian motion under that one?
But what is a Brownian motion depends on what measure you're under.
Right, but I'm saying is like the theorem allows us to change what measure it's on.
Yes.
And I mean, because I remember when we defined Brownian motion, right? We had like the path properties and like the distributional properties.
Yes.
Is it be does the measure like implicitly determine like in that definition because of the normal distribution you have when you do like BT minus BS has to be normal?
Under a measure, right?
Yeah, that's what it's implicitly in that in that part of the definition,
Yes.
right?
But it's
Okay.
also independence, right? You can be independent on the one measure and you won't be independent on an equivalent measure.
Okay. Okay. The increments, I see.
Right? There are a number of properties that have to hold, and some of them are path properties and some of them are distributional properties. And the distributional properties, they all vary with the measure. And just because you have two equivalent measures, it doesn't mean that you stay normal or anything like that. It's not true.
I see. Okay. But doing this calculation with Giordano's theorem allows us to know that it's true under some other equivalent measure.
Right. So what Giordano's theorem tells you is if you want to create a new Brownian motion under an equivalent measure, it tells you what the correction term is.
Oh, okay. I got you.
Right? That
I see.
Brownian motion that you start out with, it is not going to be a Brownian motion when you change the measure to an equivalent one. Just look at the first example we did. If this B here were to stay a Brownian motion under a P tilde, we could never get a T on the right-hand side. Because if BT were to stay a Brownian motion on the P tilde, you would always get 0 on the right-hand side.
I see. Okay.
Right? When you're on the P, this is a Brownian motion, expectation is always equal to 0. Now you change to an equivalent measure, and we don't know what, I mean, this B here is not Brownian motion on the P tilde. Right? Giordano's theorem tells you exactly what you need to correct B with to get Brownian motion on the P tilde. So what Giordano's theorem tells you is that these correction terms, they have a very specific form and they're related to this Radon-Nikodym derivative process. Does that make sense?
Yeah. Hold on. So it becomes T. Is T the correction? So when we say E with respect to the expectation with respect to P tilde of BT is equal to T, that T popped out because it was like some correction term happened.
Yeah, I mean, that was the goal, right? You
Okay, yeah.
made a measure such that this is true.
Okay, so and when in the part where it says Gersanov says this statement, yeah. The dp tilde over dp, is that the Radon-Nikodym derivative process?
Yeah,
Or is that something?
I
Okay.
mean, this is the Radon-Nikodym derivative, right? So to get a process, you need to have something indexed by time.
I see.
So the Radon-Nikodym derivative process is this thing down here. Because now there's a time, right? So you need to tell me what the Radon-Nikodym derivative is on all these sigma algebras you have in the filtration. Then this is going to give you a process.
Okay, I see.
There are other questions or comments? I had one more example prepared. So let's do that one. Call it night. So the last one was 12.1.
Wait, Professor, can you go back to the last page we were working on?
Yeah.
It was cut off by the camera.
Ah,
Right.
okay.
Thank you. All good. Thank you.
So then the last one was question 12.1. Let me try to do that one. 12.1. If you read these questions, you can start seeing that it has a lot to do with asset pricing, right? You can see, for example, in question number 12, like now there's a DS. That's probably a stock price. There's an S0 here. This is probably the money market account. And now it starts talking about wealth processes further down. Right, so we are almost there. I think it was Ibrahim who said a few times ago that he would like to get to derivative pricing as soon as possible. So we're almost there, right? We're doing the first problems in these questions that are related to derivative pricing. So here we're working with a process that has this form. So you have two Brownian motions, B and W, right? So each one is a Brownian motion, and the cross variation between them is 0. So you're starting out with these two, and then you have this DS process that's sitting here. And your goal is to find an equivalent measure such that S we have up there is a martingale. And the reason I wanted to do this one was because we've been looking at these thetas, these market price of risk. We've been looking at them. So far, they've always been constants. And so here's an example where they're not a constant. And so you're looking at DST is equal to ST, and then is mu WT squared dt plus sigma WT dBT. So we introduced the random derivative. Okay, so let's look at the process. dCt was minus z theta dBt. Well, let's see if we can figure out what theta is. So what should we choose for theta? Well, we use Gisanov theorem. We use Gisanov theorem. He says that you get a new Brownian motion. What is the measure called? Here's a Q, it's Q. So you get a new Brownian motion by taking the old one, so that one, plus the theta dt. And your job is to figure out what theta is, the market price of risk. Okay, so the way you do it is you go up to the dynamic, so you replace dB here. You just substitute in, this is going to be dBTQ minus theta dt. And you want S to be a Brownian, you want S to be a martingale. So S is a Q martingale if what? Well, if there's no drift, if there's a 0 dt, because stochastic intervals are martingales, we drop the dt term. So can we cancel out the dt terms? Well, we have mu WT squared minus sigma W times theta. I want this to be 0. So I want theta to be we'll solve the equation for theta.
WT squared. Yeah, new WT. Oh, new WT. Sorry. Yeah.
So this is now no longer constant, right? This is a stochastic process for theta. So the question goes a little bit further. So this year is going to work. It says the question actually asks you to specify every measure in the entire world that satisfies that this S we have up here is a martingale. And so we can actually we can find more. There are more measures. There are more equivalent. There are more equivalent measures because, and this is because Ft is equal to the the filtration that both B and W generate. So when you have two Brownian motions, you count the number of Brownian motions in the filtration. Here there are two. So you should have two market prices of risks. We only determined one. So because there are two Brownian motions, it's these two here that go into there being two market prices of risk. We have two Brownian motions, they're going to be two market prices of risk, one for each Brownian motion. And so the more general form of Z is, so now we're moving into the two-dimensional Gisanov theorem. So for the two-dimensional Gisanov theorem, you'll have dCt is equal to what we have up here, minus Z. And then you put a parentheses, and you have your theta, and then it's dB, plus something else that's called a psi, and then dW. And these are your two market prices of risk. And then what Gisanov's theorem tells you is, he says that this pair, where you take the market price of risk for the first one, the market price of risk for the first one, that's the correction term. But now, Alice, there are two correction terms. There is also one that has to come in for the other Brownian motion. And the other one gets corrected with this second market price of risk. Gisanov's theorem says that these are Brownian motions. And you can see the cross variation between them. If I look at BQ and WQ, this is going to be exactly the cross variation, because here we have DT terms, they won't matter for the cross variation. So this will be the same as B and W, which is 0. So if we were to include this psi here, you can see up here that there's no dW term. There's only W sitting in here as a coefficient. So if you wanted to have all the meshes in the entire world, then all meshes under which S is a martingale, they have the form, they have a Radon-Nikodym derivative processes. You'll have your dCt is equal to minus Ct, and then the market price of risk that we cooked up in the first part, this one. So that will be your mu Wt over sigma dBt. And then the other one is free. And this one is free. So if you wanted all the meshes in the entire world that would satisfy that S is a martingale, they would all have this form down here.
Professor.
Yep.
So, the thing you wrote on the bottom of the page right before this, there was like, is that f of t to filtration?
Yes.
So we were saying we want a filtration where the small sigma algebra has, oh, okay, includes both the Brownian motion of B and W.
Yes. I mean, that's given in the problem. That is input. You see here it says let B and W be two independent.
Oh, okay, I see.
Is this?
Can you explain the statement about BQ comma WQ equals BW?
This one?
Hold on, let me. Yeah, that one.
This is the credit variation, right?
Yes.
So if I take the credit variation between two processes, the only thing that you have to look for is where the rounding motions are. Right, so I have the B here and I have a theta here, but that's being multiplied onto dt. dt is never going to enter into these higher order variations. It's only going to be the rounding motions that matter. So if you want to compute the cross variation between two of these processes, I'll just have to focus on where the rounding motions are.
Okay, because the DT terms don't count, so there's zero.
So I only have to worry about these two. So that's why.
Okay, so then you check the cross variation between BT and B and W, and that's 0 because
I mean, that's given. This is again,
it's given.
given.
I see.
And given what it says, you have two independent one-dimensional Brownian motions, B and W. So that's where the zero cross variation is coming from. So
Gotcha.
we haven't talked about the connection between independence and this zero cross variation of Brownian motions. Maybe we should do that at some point. But yeah, this is that word independent here. This is the key word that will give you this zero cross variation.
Generally, where would you say, like, in this big book we are right now in the past, like, 2 weeks?
I actually updated our syllabus, so I can show you how that goes. If you go to, I hope I uploaded it, as Ibrahim pointed out, I think a few times ago. Sometimes I don't hit the upload button, and I hope this didn't happen this time. But if you go to modules,
It was there this time. I saw it.
it was there this time.
Oh, okay. There's a new one.
If you grab this November 22nd syllabus, it's there all the way at the bottom. So change of measure, we are working on chapter 5.2, Kisama's theorem. And we've been doing a number of examples. And next time we're going to move on and start talking about hedging and pricing.
Gotcha. Thank you.
I got a new computer and it changes colors depending on the day. I don't know if this is what all new computers do, or if I hit a button somewhere, my screen is now mostly black.
No, this is the new update. On, I think you have a Mac. Yeah, you do. That's why it happens.
But it changed.
Do you have flux on the top? I see the little, like, the circle with the sine wave.
Yeah, I have flux on it, but I mean the black thing. This, I mean.
Oh, you mean night mode for
Yeah.
the okay. I thought you meant like the orange because, like, to get rid of the blue light.
I mean, otherwise I can't sleep at night. So that's just, yeah.
Professor, can you scroll to the last thing? Okay, perfect. Thank you. Okay. I have a few questions about the homework. I think office hours may be the best bet, but I tried for several hours and I was having trouble getting through the first problem.
Let me see if I can help out. So let me just bring up the homework. This is number 9.
Yes.
So for the first part, so the first thing you need to do is to figure out what are the dynamics of this process in question. Right? So you need to look at d of s divided by S0, because that's the thing that you want to be a martingale.
Okay.
And so keep in mind here, there's no Brownian motion is a 0, right? That's the ultimately the bank account.
Mhm.
There's no Brownian motion there. So what you will have is you could be able to put him outside, and then right. So ST is 0. This is this. This has an ODE, right? This is going to be S0, 0 times the exponential, and then an interval from 0 to t of RU du. Right, yes, yeah, that's the ODE. So you can see now if I do 1 over it, so if I do 1 over it, you're just going to get a minus sign here. So when you apply Ito's lemma, ultimately what you're going to get is this is going to be this minus r that's going to come down, and then you're going to have the dynamics of S. So that'll be your mu t dt plus your sigma t dwt. And so now the name of the game is you specify your random economic derivative dct1. How many Brownian motions do we have? There should be an ft defined somewhere, be the filtration generated by a Brownian motion w. So there's exactly one Brownian motion. You want to write this here with your minus your theta ct1 dwt. And had there been more Brownian motions in the filtration, you're going to need more terms over here. And so Gisanov says that you get a new Brownian motion by taking the old one, and then you add your theta dt. And your job is to figure out what this theta is. So the way you do it is you take this thing here, plug it in up here. dw is going to become dwtq minus your theta dt. And so you want st over st0. This is a martingale. If and only if there's a CODT, this happens if and only if. You look at all the dt terms, you will have mu. You have your minus r. You have your minus, there's a sigma out there. Then there's your theta. You want this to be 0. And so you solve for theta. It's mu t minus rt divided by sigma t.
Can you center the page, please? Okay, so we needed today's lecture to be able to do this, right?
Because we fell behind on the.
Okay. So can you please make the homework due Sunday?
Yeah, we can do that.
All right. Thank you.
Yeah. The important thing, Ibrahim, is not. The important thing is that you guys are going to be able to do this stuff here. This is that's the important thing.
Yes. I feel like, I mean, this is definitely a step above the previous exams material. Do you have any recommendations as to where to? I guess I'll ask you this in office hours, but I was just having trouble with the earlier stuff when I was trying to practice the exam, computing like first variation, second quadratic variation.
Yeah, there's no doubt that this continuous time finance here, this is the step up. This is not easy, and we do not have very much time to go through it.
That's true.
So we're trying to make the best of it here.
Yeah.
And the way that my impression was that there were several students that asked for more examples So I'm trying to go through example after example after example to get you guys to be able to like see how you apply this material, and then focus less on taking you guys through the proofs. So there are a number of problems that one just has to go through before you become fluent in this. That being said, I've seen many undergraduates being able to do this after a few weeks of practice. As you have noticed, and as many of you have noticed, I mean, we are doing the same thing over and over, and now we're seeing Gesano's theorem for the first time. So that takes a little bit of time to get used to. But you will get to exactly the same point as you have done with so many of the other things in class, to be doing the same thing over and over and over. It's just right now we're starting out on a new thing that we're going to be doing over and over and over. So I believe we can all get there, but I also understand that this is a step up from a lot of the earlier material.
I definitely agree with the examples today. I think I was able to see how to at least proceed with solving some of these problems. So maybe that's what we needed to do for
Well,
understanding.
let's try to do some of these problems and then see how it goes. And if you get stuck on it, then office hours on Thursday and Friday, and try again next week.
All right.
No problem pushing the homework. This is fine. We fell behind before Thanksgiving, and yeah.
Thank you very much. Have a good night.
Alrighty, guys. I think it's time to call it quits. Office hours on Thursday and Friday morning, and of course we'll have a lecture on Thursday night. All right. Have a good night, guys.